Just give me a second. Yeah. So we have a causal chain here. So you have x to y, y to z, and z to w. Now, if you want to compute the joint distribution of these variables, so you can write simply them that in a chain rule like this, right? Now you can see that we can make conditional independence assumption, like say this probability z given x y is equal to probability z given y. So that means if we know y, then z no longer depends on x, right? So z and x, they become conditionally independent. So this is something similar to what we have talked about, like say past, and you have current and future, right? So if we know the present, the future does not depend on past, something like that, right? Similarly, if we know z, then w no longer depends on y and x. So that means we can simplify these conditional probability w given x, y, z to be probability wz. So this is what we have done earlier, right? Now let me take out a triple, which is your x, y, and z, and represent it here, right? So x, y is dependent on x, z is dependent on y. Now the question I'm trying to ask, whether x and z are truly independent. So by the rule of transitivity, if I say x affects y and y affects z, so you can say that x affects z. So one such example, let us assume that x is low pressure, y is rain, and z is traffic. So what I can say, low pressure causes rain and rain causes traffic. So can we not say that low pressure causes traffic? But as soon as I know that there is rain, whether there is low pressure or not, I really don't care. The traffic only depends on y, that is rain. Now the rain can be caused by low pressure. Rain can be caused by maybe a very small terrestrial rain, something like that. But as soon as I know that there is rain, this traffic no longer depends on whether there is low pressure or not. And that is what we call as separation of two variables. We are separating out two variables x and y, given that we have got evidence on an intermediate variable. And that is what we call as deseparation, which is a study of independence between a pair of variables given another variable, right? Now first, so we'll be talking about three patterns. One is causal chain, the second is common effect, and the third one is common cause, right? And for three of these, we'll be using this example that we have talked about earlier. Low pressure may cause rain and rain may cause traffic. So LRT, right? Now, if we look at the conditional independence, so this P LRT can be written as PL, PR given L, and PT given R, right? So from this Bayesian network, we can do this, right? Now, first thing that I am to ask whether L and T are independent or not. So I do not observe anything. This is simply this Bayesian network, and from this network, I just want to ask whether L and T are independent or not. So of course they are not independent, because low pressure causes rain and rain causes traffic. I will say low pressure causes traffic, right? So what is being done? The influence of L is being passed from L to T through R. So there is a flow of influence or information from L to T. Now, if you have a flow of information from one node to the other node, so that brings us to the notion that these two are not independent, because they have a path between them. right? Now let's say we ask a different question, whether L and T are independent given R. So now we observe R. So by intuition, we know that these two now becomes independent. These two, L and T, now become independent. T only depends on whether there is rain or not. I know that there is a rain. So that means this T no longer depends on L. So how do we model this? We model this as whenever in a causal chain, we have observed an intermediate node, the information flow is broken here. So the information cannot pass through the node for which we have got evidence. Now, as we do not have a flow of information from L to T, then these two are independent of each other. So this is how we model these kind of intuition that we are talking about, right? So basically, we can represent T given LR to be the joint distribution PLRT divided by PLR, and we can rewrite this as from the Bayesian network PL, PR given L, PT given R, and this is your P L, PLR given L, and you can see that these can be crossed, these can be crossed to get PTR. So that means these T and L, they are independent of each other, right? So this is one. What is the takeaway from this example discussion? So the takeaway is that whenever you have a chain of causation, so if you have an evidence on one of the nodes in between, then the influence or information from the source to the destination is blocked, right? So this is what we get. The second thing that I'll like to talk about is the common cause. So let's say we have got another variable. We have a overflown lawn, right? And we represent that with variable O. Now, if there is a rain, my lawn may be overflown. And if there is a rain, there might be traffic, right? So the first question that we will like to ask. So again, how do we represent this PORT? PORT is basically PR given multiply PO given R multiply PT given R, right? So this is basically coming from directly from the Bayesian network, right? Now the first question is whether O and T are independent. Of course, they are not independent because this overflown lawn and traffic, they are somehow correlated in some cases. So there might be certain probability they are correlated with each other. So they are not. So how do we model that? So basically, whenever I have not seen any evidence, so evidence is on the common cause. I haven't seen any evidence. So there is a flow of information between these two nodes. So here we are not really looking at the directionality, right? So we are treating this network to be undirected and trying to see whether there is a path from this node to this node and vice versa. If there is not, then they are independent. They are dependent, right? Now we ask the other question, like whether O and T are independent given R, right? So whenever now I see R, so that means there is a rain. So these two becomes independent of each other. So what is the test of independence? The test of independence is, well, I know the value of R, right? I predict whether my lawn is overflown or not. So I have certain probability, right? Now I understand that there is a traffic. So this was kept in my in the envelope in my pocket. This is your Y. Now I open it. I know there is a traffic. Will that change my belief in overflown lawn? I think not, right? So that means they are independent, conditionally independent given the value of R, right? So again, we can write PT given OR and we can derive this PTR. So that means T and O are conditionally independent given R. So what is the takeaway from here? So if we have observed the cause node, so this is our causation node. So if we observe the common cause, so that will block the path between the effects. So this is what we see. So the path between these two will be broken if we observe the common cause. So this is the second takeaway. Structure is a bit weird, and I think it will take some time to understand it, which we call as the common effect. So let's say you have variable traffic, right? If there is rain, rain may cause traffic, and say that there is an IPL match going on in your city, and that might also cause traffic, right? Now let me ask the question whether R and M are independent. So my take on this would be yes. So one might argue that, well, if there is a rain, then the match will be abandoned or like something like that. So let us not take that into account, right? But the decision that the match is being played and there is a rain, these are two completely independent events, right? So what does that mean? That means that there is a flow of information. The flow of information from R to M is not there. If the flow of information from R to M or M to R were there, then these two would have been dependent. But at this very observation, we have to block this information flow, right? So what does that give? That gives us the notion that whenever this common effect is not observed, the common effect is not observed, then the information flow from R to M is blocked. So this is a kind of contrary to the thing that we have done in the earlier two patterns. There, if we had observed the node like this, then the information flow was being blocked. So this is a kind of difference or contrast that we are having here, right? And this is also called a V structure. You can see a V like this, right? This is also called a V structure. Now let us look at the other question, whether R and M are independent given T. So my answer is no. So what do you think? Can you give an argument in support of this? Just consider this envelope thing. So what is our Z? Z is equal to T. Sorry. Yeah, Z is equal to T, whether there is traffic or not, right? What is my X? X is rain, right? What is my Y? Y is M, right? Now, I know this. There is traffic, right? And from this, I can predict the value of X. So let's say there is some probability that there is rain, right? Now, I know that I open the envelope N, right? And I see that N is false. So there is no match. So that makes the case that certain that there is rain. So the probability of rain goes very high after I know that there is no match, because I know that these two are the causes of the traffic. And if I eliminate this cause, so that means the confidence on these becomes a bit higher. And what is the kind of thing that we are getting into? We are getting into a thing that there is an update of belief on the probability of rain given that M is match is not being played, right? So the knowing the value of y that was there inside the envelope has changed the belief in x, right? And if that happens, then R and M or X and Y, they are not independent, right? So basically you can see here R and M, they are kind of competing explanation for the traffic. As their competing explanations, they are now dependent on each other, given that we have seen observed traffic, right? Now, how to model this? So basically, when we observe this T, so this gate will be opened. So you can imagine that there is a gate here. Now, as soon as we observe this traffic to be true, then this gate is opened and there is a flow of information between R and M. And as there is a flow of information between R and M, these two events are variables are not independent. They are becoming dependent on each other, right? So these are the kind of three structure that will give us the sense whether two events or two random variables are independent or not. So let us play with a structure like this. I think if you can understand, then you will be able to answer. Right? So let us say this is the overall Bayesian network. We have combined the different structures earlier that we have seen. Only thing that we have added here that if there is a traffic, maybe there is a traffic report T prime. So this is the only addition, right? So there is, I don't know, I have changed it. So this is M. Okay. Now, when let's say we want to find out whether L and T, they are conditionally independent or not. So what we'll try to see, we'll try to find an undirected path from L to T prime. And if we see that none of the part, so this path is a kind of set of segments. And if none of the segment is blocked, then we can see that there is an information flow from L to T prime. And if there is an information flow in this path, then we can say that these two are conditioned, these two are dependent on each other, right? Now, if the path breaks in presence of an evidence node, as we have seen earlier, then these L and T prime will be unreachable with respect to each other. As they're unreachable, the information cannot flow between them. And as that cannot be done, they are becoming independent of each other, right? So that is the kind of notion of deseparation. But for the V structure, the kind of thing is opposite. So as we observe the V structure, the gate is opened, right? And if we don't see the V structure, we have a gate that is closed here and that will be blocking the path here, right? So that is the kind of thing that will be seen, right? So let us try to summarize the observation that we have done earlier. So our test is to see whether, X and Y are independent of each other given Z, right? And we say this is yes, if X and Y are deseparated by Z, right? And how do we find out whether they are deseparated or not? We just try to see whether there is no active path between X and Y, considering all the possible paths between X and Y. So if there is no active path between them, so let's say you have got X and Y, and let's say you have a path here, you have another path here, and you have another path here. And if you see that all the paths are blocked, then they are deseparated, right? And how we will check the path? So for the path, we'll check each triple that is there in the path, right? So you have a triple like this, as we have considered earlier. And for each pattern, we'll be deciding something. So we have, if we take causal chain like X to Y to Z, so the active triple will be having this pattern, right? But the inactive triple will be having this pattern where we have observed the middle one, right? Common cause. If the common cause is observed, it will block the evidence. So we'll not be having a flow between these two. Then the path triple will become inactive, and if the triple become inactive, that path will become inactive. But that is kind of reverse in the case of common effect, where if we see the common effect, so that will activate the path between them, right? And if we do not see it, then that will be blocked. And that is a kind of extension to this pattern. If we have a kind of descendant of this node, let us call this to be V node. If we have a descendant of a V node and that descendant it is observed, then this gate is opened. So even though this is not observed, but one of its descendant has been observed, in that case also we have a flow of information. So this is a kind of extension of the basic V structure, right? So these are the kind of few patterns which we'll be using to decide whether two events or two variables are conditionally independent or not. So let us take this example, R, M, T, T prime. So the first question that we like to ask whether R and M, they are independent or not. So can you tell me whether they are independent or not?
Yes, sir.
They will be independent. Any other response? Why do you say it will be independent? You look at the structure. This is the V structure, right? So when we have so if they are independent, so that means there is a blockage, right? So you have not observed this. As you have not observed this, there will be a blockage. So that means information does not flow. So that means this is independent. Right. So next case, the next case is whether they're independent given T. So what would be your answer? Now we have observed T.
Not independent.
They are not independent. So let us write it to be dependent. Are independent M given T prime? What would be our answer?
Dependent.
So we have observed this now. So it is a kind of second case of V structure, and this will give us dependent, because there will be an information flow. Right. This is another example. We like to ask whether L and T prime, they are independent of each other given T. So what we have observed this, right? So what is your response? Whether L and T are conditionally independent given T.
No, dependent.
So you have to check this path, L to T prime. So this is not blocked. We have an information flow here. And as we have observed this, and this is a V node, we have an information flow here. So they will be dependent, right? Let us do it for, say, L and M. Are they independent? This and this. So the scenario is this. Are they independent?
Yes, sir. Independent.
They are independent because this is a V node and our path will be blocked here. So it will be independent. And similarly, you can do it for this, and let me tell. So what would be this? L and M given T and R. So you have observed T and R.
Independent.
They will be independent. Right? Now let's take a case where you have got multiple paths. So you need to take into account multiple paths also, because your Bayesian network may not always be having a single path between two variables, right? So for this, we have got another variable which is stuck at home, H. So if you have overflown lawn, or if there is a traffic, you are stuck at home, right? Now let me ask whether P and O are independent of each other. What would be your answer? Are they independent? Any idea? So you need to check paths, right? So let us consider this path. So is this blocked or it is open?
Open.
It is open. I have not observed anything.
Sir, it is blocked, right?
It is blocked. It is a V structure.
Yeah, so it will be independent.
But you have to look at this path. This path is open, right?
Oh, right, right.
So this will be dependent. So at least one path is open, right? So let us consider the other case. V independent O given R. Now we have observed this. So what would be answer here?
Independent.
They will be independent because this path is blocked and this path is blocked here. And what would be the case where we have seen both R and H?
Dependent due to lower.
It will be dependent, right? Because there will be an information flow via this path, right? Now there is a kind of design choice that we have to make while we are talking about these conditional independences. So one possible design choice may be, well, let us assume that all the events are random variables are independent of each other, right? So will that be a good design? It will not be a good design because it might so happen that the two variables, they are dependent, but we are forcefully making them to be independent. That means these kind of assumption will be having less expressive power. So it will not be able to define your joint distribution properly, right? If you are making an assumption like this. So let us consider that this is a kind of joint distribution, this kind of structure that it can express, right? Now skip this. So the other extreme is that you define everything to be dependent on each other. So you do not have any independence assumption. You do not have any CI here, right? Now, what does that mean? That means it is very expressive. But at the cost of what? Can you tell me at the cost of what? If we make them to be fully dependent on each other? What is the cost?
Number of assignments will increase.
The number of assignments will be increased, and it will be in the 2 to the power order of 2 to the power n if we have binary variables, right? But it will be more expressive, right? So neither we want this nor this. So we want to hit a middle ground where we pick up certain set of CIs and try to model them, right? And that will be kind of a middle ground. This will be a bit more expressive than the very naive representation like this, but it will be more efficient than this, but it will be less expressive than this kind of choice, right? So what is the time now? Okay. Okay, we have got a bit more time to take. So now what we have talked about, let me summarize. We have tried to see how we can make use of the conditional independence assumption to design a data structure which will be very efficient in representing the joint probability distribution of a set of random variables, right? And there we have talked about the representational issues and the different patterns and their implications. But the primary task in hand is that let's say we are given with such a network, which is a Bayesian belief network, which encodes the conditional dependence between different variables. Now, can we infer new knowledge out of this knowledge? So we are representing our knowledge base now in a probabilistic term. And given a knowledge base, we need to infer new knowledge as we did in the case of the propositional and other logic systems, which are kind of crisp domain where we have only true and false value assigned to it. But here we are assigning gradation of belief on different facts, right? And in the face of that, we'll try to see whether we can come up with new inferences out of existing knowledge base represented in the form of a graphical structure like Bayesian belief network, right? So let me introduce the probabilistic inference problem, right? So let's say we have the total set of variable which is V. So in your Bayesian network, we have V nodes. So what does that mean? We have got V variables and we have represented that in a Bayesian network. So that means we have V nodes in the Bayesian network. Now we want to compute the posterior probability of X given E1 to EM. So let me explain what are these X's and E1 to EM. So they all belong to this set of V. So these all belong to this set of V, right? Now this X is called the query variable. So this is the kind of variable we want to query. So for example, what is the probability that there is burglary when John calls and say Mary calls, right? So here burglary is the query variable and John calls, Mary calls are the evidence variables. So these E's are called the evidence variable, right? So I'll put this in a query form like this. So given the evidences E1 to EM, what is the probability of X, which is our query variable? So this is what we want to ask, right? So how do we partition this set of variable? The set of variable can be partitioned into three sets. One is the set which will consist of only the query variable. The other set, which is basically the set of evidences, and the remaining subset from V is the set of hidden variables. So these are the variables that do not appear in the query, either in the form of query variable or in the form of evidence variable. So all these partitions are disjoint partitions. So these are disjoint partitions, right? They're called hidden variable. One such example is what is the probability of burglary when Mary calls and John calls, right? Now there is another variation of this inference problem. So we have got the same Bayesian belief network with V nodes, and we want to find the most likely explanation or cause of something, right? So basically, these can be problem can be written as, so this X can have various values, X, X1, X2, X3, many things, right? And there are certain evidence variable. So I need to tell what is the kind of most plausible explanation of these evidences occurring. So for example, I have say yellow teeth, I have say something other thing. toothache, etc. And I need to predict what is the probability, what is the cause of this. So the cause can be say uh, mm, uh, cause can be say bad teeth, cause can be say other thing also, right? I need to find which is the probable cause, most probable cause. So again, this is the query variable, this is the evidence variable. So one can think of like among burglary and earthquake, which is the most probable explanation, both Mary and John call, right? So with this, let us now focus on the solution of these problems, right? So the first solution is the kind of brute force solution, which we call as inference by enumeration. So here we'll be enumerating all the possible values of the variables that are appearing in our computation and try to come up with certain measure which will give us the conditional probability. So I think that we can do in the next class. So for now, let me stop. And in the next class, we'll start talking about inference by enumeration. Okay. So, well, I'm done for today. So if there are any doubts or questions, I'll be happy to answer.